In this Pharmacology Concepts video module, we'll be talking about pH, pKa, and ion trapping. Since these concepts are eminently testable, they frequently appear on pharmacology exams, and they also have some real clinical applications, particularly in pharmacologically manipulating drug absorption and elimination. Also, it's fairly easy to do the calculations 180 degrees in the wrong direction if you don't have a good feel for the material to begin with. So the purpose of this video is to give you a firm foundation so that you'll be able to confidently tackle questions related to pH and drug pKa. The specific objectives of this module are that after studying the material presented here, you should be able to derive the Henderson Hasselbalch equation from the definition of Ka, the acid dissociation constant, calculate the ratio of a drug's protonated and deprotonated forms if given the pH of a solution and the drug's pKa, and to predict the effects of drug partitioning and elimination caused by pharmacologic manipulation of the pH of body fluid compartments. First off, you need to know that many drugs are either weak acids or weak bases, and those that are weak acids tend to be so because they contain carboxylic acid groups, while those that are weak bases tend to be so because they contain amine groups. The example given here is aspirin, or acetylsalicylic acid. In an aqueous solution, the uncharged form of aspirin, denoted as HA, will partially dissociate into its conjugate base, A-, and a proton, and some equilibrium will be reached. Pretty simple chemistry going on here. On the other hand, you might have a drug that is a weak base, and the example given here is amphetamine. And the fact that this drug contains an amine group is right there in its chemical name, amphetamine. In an aqueous solution, amphetamine can exist in an uncharged or free base form, denoted as B, or it may be protonated to its corresponding ammonium ion, or BH+. But you can see how this equation is virtually equivalent to what we just saw on the previous slide. Both drugs can exist in either a deprotonated or protonated form. The difference, though, between a weak acid and a weak base is whether it is the protonated or deprotonated form that is ionized or charged, and therefore more water-soluble, and which is unionized, which would be more lipid-soluble. The thing that makes a weak acid or base weak is that it will not be fully dissociated at physiologic pH ranges. A strong acid like HCl, hydrochloric acid, will completely dissociate into H+ and Cl- ions when added to water, whereas a weak acid like carbonic acid, H2CO3, will partially dissociate such that the resultant solution at equilibrium will contain H2CO3 and HCO3- and H+ ions. And it's the ratio between the amount of H2CO3 and HCO3- that's interesting and is something that we should be able to calculate. It's the Henderson Hasselbalch equation that describes the relative amount of a weak acid and its conjugate base in an aqueous solution. With regard to pharmacology, Henderson Hasselbalch states that the pH of a body fluid is equal to the pKa of the drug plus the logarithm of the concentration of the drug's conjugate base divided by the conjugate acid form. And with weak acids and bases, both forms of the drug can be found within the physiologic pH range. Hopefully, just from looking at this equation, you can begin to predict what kinds of mathematical calculations you might be expected to perform, but we'll be going over a few more examples later on in this video. So let's define some terms here. Ka, the acid dissociation constant, is determined by the concentrations of HA, A-, and H+ at equilibrium. These concentrations can be measured experimentally and the value for Ka defined for a given acid. Like any chemical dissociation constant, the Ka is equal to the concentrations of the products multiplied together divided by the concentration of the starting chemical. Now what Henderson, of Henderson Hasselbalch fame, did was to rearrange this equation for when the acid in question is CO2, which we know can combine with water to form carbonic acid, and which can then dissociate into bicarbonate, HCO3, and H+. So here's a picture of Lawrence Joseph Henderson, who studied the buffering power of carbon dioxide in the early 20th century. While the math on this slide is not difficult, it's not something that you need to memorize. The main point here is to give some historical background. Henderson took the equation that defines Ka, and for the case where the acid is CO2, he rearranged it to yield the Henderson equation, where the concentration of H+ times bicarbonate equals a constant, K, times the carbon dioxide concentration multiplied by the concentration of water. This is just a slight variation of the definition of an equilibrium constant. Since the concentration of water in an aqueous solution is constant, And since the concentration of carbon dioxide in solution is proportional to its partial pressure, the equation can be rearranged to a revised constant multiplied by the partial pressure of CO2. Now, Henderson is an interesting figure in the history of medicine, and he's been attributed with a wonderful quote stating that somewhere between 1910 and 1912 in this country, a random patient with a random disease, consulting a doctor chosen at random, had, for the first time in the history of mankind, a better than 50-50 chance of profiting from the encounter. At around the same time, the Danish chemist Søren Sørenson developed the pH scale. pH basically means the power of hydrogen, and putting the letter P in front of a chemical concentration means that you are looking at the negative log 10 of that concentration. Thus, pH equals the negative log 10 of the hydrogen ion concentration in a solution. And you can put the letter P in front of any concentration or any variable if you wanted to, so we can talk about pKa, which would be the negative log 10 of the acid dissociation constant of any given chemical. Just a few years later, Karl Hasselbalch, another Danish scientist, applied Sørensen's terminology to Henderson's equation to derive the Henderson Hasselbalch equation. This is fairly straightforward math as long as you understand logarithms, but I think being able to derive the Henderson Hasselbalch equation from the definition of Ka helps to solidify the relevant concepts in your brain and means that your calculations about weak acids and bases are more likely to be done correctly. If you can't recreate this derivation, you're probably going to have trouble with this topic. So we start with the definition of Ka as H plus times A minus divided by HA. Then we take the base 10 logarithm of both sides. Then we slightly rearrange to remove the H plus term. This is the part where you have to remember that adding logarithms is the same as multiplying things together. Next, we apply the step from Sørensen where the P of anything is negative log 10 of that thing, replacing log 10 Ka with negative pKa and log 10 H plus with negative pH. Then we rearrange again to yield pH equals pKa plus log A minus over HA, the Henderson Hasselbalch equation. So what's so special about the value of pKa? From the Henderson Hasselbalch equation, we learn that the pKa is the pH at which an acid is half dissociated. If the concentration of A minus equals the concentration of HA, then the final term in the equation is 0. 10 to the 0 power is 1, so the logarithm of 1 is 0. And the pH will equal the pKa when the concentration of A minus equals the concentration of HA. But if you play with the numbers a little bit, you find that if the pH of the solution is less than the pKa, meaning it's a more acidic environment, HA will predominate since the final term has to be a negative number, and that would occur if HA is greater than A minus. And if the pH is greater than the pKa, then A minus, the conjugate ionized base, will predominate. Drugs that are weak bases work the same way, but in this case, pH equals pKa plus the log of B over BH plus. BH plus is the acid, so to speak, in this case, because the definition of an acid is that it can donate an H plus ion. So if we're talking about the pKa of a weak base, again, the concentration of the conjugate base will equal the concentration of the conjugate acid when pH equals pKa, because the final term in the Henderson Hasselbalch equation will be 0. And if the pH of the solution is less than the pKa, then BH plus, a charged ion, will predominate. And if the pH is greater than the pKa, then the uncharged B will predominate. This slide is to give you a general idea of what pKa values we think of with drugs that are weak acids or bases. Weak acids generally have a pKa less than 7, the pH of a neutral solution. Here we see the dissociation of a carboxylic acid. The pKa of this carboxylic acid happens to be 4.8, and the pKa of various other carboxylic acids tends to be in the range around 4. The pKa of weak bases will generally be greater than 7. Most protonated amines, the conjugate form of a weak nitrogenous base, have pKa values around 9 to 10. It is possible, though, and not that uncommon, to have weak acids with pKa's greater than 7 and weak bases with pKa's less than 7. This all depends on the various electrochemical forces around the proton donating site for acids and the proton accepting site for bases. So perhaps a better definition of an acid is a neutral molecule that can potentially dissociate into a charged anion and a proton, while a base is a neutral molecule that can potentially combine with a proton to form a charged cation. Here we see two illustrative examples that you definitely don't need to memorize now. On the left is phenytoin, a common anticonvulsant medication, which is a weak acid that has a pKa of 8.3. The hydrogen ion that it can potentially donate is not part of a carboxylic acid group, which helps to explain why the pKa is so much different than for other carboxylic acids. And on the right is diazepam, a common sedative hypnotic medication, which is a weak base with a low pKa of around 3. The nitrogen atom that has a free electron pair to potentially bind a proton does so less avidly than the nitrogens and amine groups in many other molecules. This is a graphic representation of what we just covered 4 slides ago. Lactic acid has a pKa of 3.86, and we see an equal amount of lactic acid and lactate ion when the pH of the solution is 3.86. If we look at lower pH values, we see that HA, the protonated and uncharged lactic acid, predominates, and if we go to higher pH values, we see higher concentrations of the charged lactate ion. So weak acids are mostly uncharged and protonated at low pH, and are mostly charged and deprotonated at higher pH. But what is low and what is high? Low means lower than the pKa, and high means higher than the pKa. In fact, we can exactly calculate the relative amounts of HA and A- if we are given the pH of the solution and the drug pKa. In the first column of this table, we see the difference between pH and pKa, and you may well be asked to determine the ratio of HA to A- if this difference is an integer. It's a lot less likely, though, that you'll be asked for exact results if this difference is not an integer, since you'd need to use a calculator with logarithmic functions. The third column here again shows that HA, the protonated uncharged form of a weak acid, will predominate at lower pH levels, and the fourth column shows that A-, the deprotonated charged form, predominates at higher pH levels. Here's a specific example. Aspirin is a weak acid with a pKa of 3.5, and we'll put it in the stomach where we'll say the pH is 2.5. Notice that in this example, the pH is an integer away from the pKa to ensure that the math is going to be easier. The pH minus pKa equals -1 in this case, and so the ratio of HA to A- will be 10 to 1. HA, the protonated uncharged form, will predominate and will account for 90.9% of the total amount of the drug present in the stomach lumen, and there will be 9.1% found as the acetylsalicylate ion. Another way of looking at this is that the low pH, a high H+ concentration, in the stomach lumen drives the depicted reaction to the right. This is just a demonstration of Le Chatelier's principle that you learned in high school chemistry. Okay, great. That's all well and good, but what the heck does it really mean? Of what practical use is the Henderson Hasselbalch equation? With knowledge of a drug's pKa, body fluid pH, and the Henderson Hasselbalch equation, we can determine where along the GI tract an oral drug is best absorbed, the relative drug concentrations in various body fluid compartments, which is called drug partitioning, and how pharmacologically manipulating the pH of body fluid compartments can affect drug partitioning and drug elimination kinetics through a process called ion trapping. The key to all these points is that uncharged molecules can equilibrate across the lipid bilayer cell membranes, but charged ions can't. The ionized forms of drugs that are weak acids or bases are stuck in whatever aqueous body fluid compartment they find themselves in. This might be in the lumen of a hollow organ, such as the GI tract or urinary bladder, or it might be within the intracellular or extracellular fluid. But the uncharged forms, being more lipid-soluble, can potentially equilibrate across membranes. And remember that this means weak acids in a lower pH environment and weak bases in a higher pH environment, where lower means lower than the pKa and higher means higher than the pKa of that drug. For instance, we can predict where oral drugs will be primarily absorbed from the GI tract based on drug pKa and pH. As we already saw, since the pH of the stomach is low, due to secretion of hydrochloric acid by parietal cells, this pushes the dissociation equilibrium of weak acids towards the uncharged and therefore more readily absorbable form. So aspirin and other drugs that are weak acids are expected to be absorbed well through the stomach lining. Drugs that are weak bases will be virtually completely protonated and charged and won't be absorbed well from the stomach. The lumen of the small intestine, however, is much closer to pH neutral. Both weak acids, pKa of 4-ish, and weak bases, pKa often 9-ish, can be predominantly in their charged forms in aqueous solution at neutral pH. However, the much larger surface area of the small intestine means that much drug absorption occurs here pretty much regardless of the drug pKa. Even if a drug might be predominantly ionized, there is still some fraction that is uncharged and can be more easily absorbed. Now we're going to do a number of calculations over the next several slides, again using aspirin as our model drug, which has a pKa of 3.5. What would the ratio of HA to A minus B in the stomach at pH 1.5? I recommend stopping the video here and see if you can do this on your own before proceeding. Okay, now we're back. We set this up by using the Henderson Hasselbalch equation such that the pH 1.5 equals the pKa 3.5 plus the log of A minus over HA. We simplify by subtracting 3.5 from both sides such that negative 2 equals the log of A minus over HA. Then we take the anti-log of both sides, which is 10 to the negative 2 power, or 0.01, equals A minus over HA. Rearrange that to get 0.01 HA equals A minus, or the ratio of HA to A minus equals 100. The uncharged conjugate acid predominates, and we get good drug absorption from the acid environment of the stomach. Now let's calculate what happens to the HA to A minus ratio after the aspirin is absorbed into the blood, where the normal physiologic pH is 7.4. Again, why don't you stop the video here and do the calculation before starting back up. So now we get pH 7.4 equals the pKa 3.5 plus the log of A minus over HA. Again, we subtract 3.5 from both sides, yielding 3.9 equals the log of A minus over HA. Then we take the anti-log of both sides, which is 10 to the 3.9th, or almost 4th, power, equals A minus over HA. Almost 10,000 times HA equals A minus. In fact, the actual number is 7943, but you probably won't need to be able to calculate these things exactly. Or the ratio of HA to A minus is about 0.0001. The charged conjugate base, the acetylsalicylate ion, predominates, and it remains in the slightly alkaline environment of the blood, while only a tiny amount of drug is reabsorbed back into the stomach lumen. So taking both of the previous slides into consideration, what's happened is that the aspirin has become trapped in the blood as the acetylsalicylate ion due to pH differences across the stomach mucosa. On the left side of this figure, in the stomach at pH 1.5, there's an equilibrium between HA and A minus that favors the uncharged conjugate acid in a ratio of 100 to 1. The uncharged conjugate acid in the stomach lumen is in equilibrium with uncharged conjugate acid in the blood since it can cross the cell membranes. But on the right side of the figure, in the blood at pH 7.4, that acid almost completely dissociates into H plus and A minus at a ratio approaching 10,000 to 1. The small purple numbers on the sides represent the relative amounts of A minus and HA that would occur at equilibrium. And from this we see that there are strong forces driving the aspirin from the acidic stomach lumen into the more alkaline blood, where the aspirin is trapped in its ionic form because it can't go back, hence ion trapping. Here we're going to discuss how aspirin partitions between blood and urine. The aspirin in the blood is going to be carried to the kidneys where it will be filtered in the glomeruli, and then it might be reabsorbed or it might not, depending on the pH. While blood pH is rather tightly controlled, there's a much wider urinary pH range. For this case, we'll assume a slightly acidic pH of 5.5. A pH of 6.0 might be more close to typical, but it can vary a lot, and 5.5 makes the math easier. On the left side of this figure, in the blood, again we see a 7,943 to 1 ratio, 10 to the 3.9th power, of A minus to HA. The small amount of HA can equilibrate between blood and urine since it's uncharged. And since the pH of the urine is exactly 2 units above the pKa of aspirin, we see a 100 to 1 ratio of A minus to HA on that side. On both sides, there is a preponderance of the deprotonated ionized form of aspirin. However, the ratio is more one-sided in the blood because that pH is further away from the drug's pKa. And that's why, at equilibrium, most of the aspirin exists as A minus in the blood, and therefore little aspirin will be excreted through the urine. However, we can manipulate the pH of some body fluid compartments pharmacologically. If we treat the patient with intravenous sodium bicarbonate, The bicarb will be filtered in the kidneys and alkalinize the urine. On the previous slide, most of the acetylsalicylate ion remained in the blood because the blood pH was further from the aspirin's pKa than the urinary pH. But now that the urine pH was increased above the blood pH, the aspirin will become ion trapped instead in the urine. This is going to greatly increase the renal elimination of aspirin, and it's a primary treatment strategy used to treat aspirin overdose. So we've seen that weak acids are better absorbed in an acidic environment, and also that weak acids can be ion trapped in an alkaline environment. Conversely, weak bases are better absorbed in basic environments, and weak bases can be ion trapped in the urine when the urinary pH is lower than the pH of surrounding tissues. The figure here is adapted from the Katzung textbook showing how methamphetamine, a weak base with a pKa of 10.0, can be ion trapped in the urine when the urine pH is relatively low. On the right side of the figure, we see that the difference between the pH and pKa is 4, meaning that the ratio of BH plus to B will be 10,000 to 1, since 10,000 is 10 to the 4th power. Because the urinary pH is further from the pKa and in the same direction as the pH of the interstitium, the methamphetamine will become ion trapped in the urine. This tendency for meth to be ion trapped in the urine can be increased by acidifying the urine, which can be aided by giving intravenous ammonium chloride. However, urinary acidification is rarely, perhaps never performed anymore to ion trap amphetamines. First off, renal clearance of amphetamines is not a major route of elimination, so even if we increase the renal clearance, the total clearance will not be increased very much. And secondly, lowering the urine pH increases the risk of kidney injury related to rhabdomyolysis, skeletal muscle breakdown. Most patients with severe amphetamine toxicity have some degree of rhabdomyolysis related to motor hyperactivity, injury, and/or hyperthermia. When muscle tissue suffers injury, it will release myoglobin into the circulation, as well as creatine kinase, which can be measured in the serum in increased levels. The myoglobin can crystallize in the renal tubules, blocking them, and leading to kidney injury, and this is more likely to occur when the pH of the urinary ultrafiltrate is low. Additionally, the iron in the heme portion of myoglobin is toxic to the kidney tubules, contributing to acute tubular necrosis. And a clinical feature seen in significant cases of rhabdomyolysis is a dark reddish-brown or cola-colored urine, and that color is due to the presence of myoglobin in the urine. And here are a couple of critical thinking questions that you can work through for additional self-assessment. And that's about it for pH, pKa, ion trapping, and the Henderson Hasselbalch equation. Hope you enjoyed.